Hey everyone, welcome to the Explainer. So think about this for a second. Why on earth would a programmer sit there and write the exact same line of code 100 times when the computer can just do it for them? Well, they wouldn't. Today, we're unlocking what is honestly one of the most powerful concepts in computer science. We're talking about iteration. It's the secret sauce that makes our code infinitely more efficient, elegant, and just dynamic. Let's get right into it. Okay, here is our roadmap for today. First, we'll look at the pure power of iteration. Then, we'll break down count-controlled for loops, followed by condition-controlled while loops. After that, things get really interesting when we combine iteration with selection, and finally, we'll wrap up with the 5 common iterative tasks you absolutely need to know. All right, let's kick things off with Section 1, the power of iteration. So why write the same code 100 times? Well, think back to when you first learned how to multiply in math class. Remember those worksheets? Your teacher probably handed you a page just packed with lots of different numbers to multiply together. Now, even though the actual numbers changed on every single line, the series of steps you took in your head to solve the problems, those remained exactly the same. You were just repeating a process. Well, programming works the exact same way. It is incredibly common for a program to deal with this massive series of inputs that all require the exact same process to be applied to them. And that brings us to our core definition. Iteration is, simply put, the programming equivalent of repetition. It lets a specific section of your code repeat multiple times, and the values can change with each pass. Honestly, it is infinitely more efficient than writing out the exact same lines of code over and over again. So instead of, say, 1,000 lines of code for 1,000 inputs, you literally might just need 5 lines of code that simply loop 1,000 times. It's a total game changer. Here we have a nice bird's eye view of our entire iteration toolkit. Basically, there are 3 main forms of iteration you'll see in most programming languages. First up, the for loop. This is your go-to when you know exactly how many times you need to iterate, or if it can be calculated up front. Second, the while loop. You use this when the number of iterations is a complete mystery, and the loop has to check a condition before it even runs. And third, the repeat until loop. It's kind of similar to the while loop, but the condition is checked after the code executes. That guarantees the loop is going to run at least one time. Okay, let's jump to Section 2 and look closely at for loops, which are our count-controlled loops. So a for loop is perfect when we know exactly how many times we need to repeat an action. But here's the thing. Count-controlled doesn't always mean it's a completely static, hard-coded number. Let me give you an example. If you want to loop some code to check figures for every month in a year, you can safely hard-code that loop to run 12 times, right? Because the number of months in a year is never going to change. But what if you're checking figures for every day in a specific month? That number fluctuates, right? From 28 up to 31. So in that scenario, the loop is still count-controlled, but the actual number of iterations is determined dynamically by a variable, usually based on user input. Let's actually look at the internal logic of a for loop in action. Check out this flowchart. It's designed to output the multiples of a given number, up to 10. See how the loop counter starts at 0? The code increments that counter, calculates the multiple, and outputs it. Then, boom, it hits a decision diamond. Is the counter greater than or equal to 10? If that's false, it just loops right back around to the top. If it's true, the loop stops. So the counter is essentially the engine that's driving the whole iteration. Now, understanding the actual anatomy of this code is absolutely crucial, especially in a language like Visual Basic. You start with for, right? That kicks off the loop. Then you have the counter, which is a variable that keeps a running record of how many iterations have run. And finally, you have next, which marks the end of that iteration section. But wait, there is a super common misconception here that catches a lot of people out. A lot of learners think that once the maximum number of iterations is reached, next acts as an immediate exit door. It actually doesn't. Next increments the counter first, sends the program back up to the top to check the criteria one more time, and only then does the loop exit if the criteria is finally outside the bounds. Kind of cool, right? Moving right along to Section 3, what if we don't have a predictable counter? That's where while loops come in, our condition-controlled loops. So these loops are built for those messy, real-world situations where the exact number of repetitions is just a complete mystery. For example, imagine repeatedly subtracting a random number from another until the result drops below 0. A for loop literally cannot handle that. On screen, we're contrasting the 2 main types of condition-controlled loops. The while loop is what we call a precondition loop. I like to think of it like a strict bouncer at a club. It checks the rules before letting any code through the door. If the conditions are false right off the bat, the loop never runs at all. On the flip side, the repeat until loop is a post-condition loop. It runs the code first and then asks if it should stop, meaning it will always run at least once. Now, with all this dynamic power comes a very real danger, and that's the infinite loop. If you write a while loop, the code inside that loop absolutely must eventually do something to make the criteria false. If you make a logical error and the condition just stays true forever, your code is going to iterate indefinitely. Your program literally gets trapped in there. No one wants that. So let's look at how to do it right. This flowchart here showcases a really practical while loop. The system is asking a user to input a series of positive numbers so it can keep a running total. Now, because we have zero clue how many numbers the user actually wants to add, a for loop is totally useless here. Instead, our loop runs while the inputted number is greater than or equal to 0. So how does the user actually stop the loop? It's simple. They just enter a negative number. That single negative input elegantly breaks the condition, stops the looping, and triggers the final output. Makes perfect sense, right? All right, section 4. To build truly powerful algorithms, just repeating steps isn't really enough. We need our loops to make smart decisions on the fly. Let's look at combining iteration and selection. We do this by nesting selection. That just means we place if statements directly inside of our loops. Let's explore this by optimizing a prime number checker. So a prime number is only divisible by 1 and itself, right? To test this in code, we typically use a modulus operation to check for remainders. But consider this. What if we input the number 120,000 to test if it's prime? If we use a basic for loop, the code checks if it's divisible by 2. It instantly realizes, nope, not prime. But that basic for loop will stubbornly continue to iterate 59,998 more times for absolutely no reason. Talk about a massive waste of computing power. But by using an if statement and a Boolean flag inside a while loop, we can trigger an early exit the exact millisecond we find a clean division. We literally only need to test up to half the input value. And here is that nesting concept visualized for you. Notice how the decision diamond for the if statement, the part checking if the modulus equals 0, lives completely inside the larger loop structure. So on every single pass of the iteration, that selection criteria is in there, actively evaluating the data. Okay, now that we've got our theoretical building blocks sorted out, let's see how they actually apply to the daily life of a programmer. Section 5, Common Iterative Tasks. There are 5 essential iterative tasks that, honestly, every computer science student just has to master. We've got totaling, which is calculating a running sum, counting, which is tallying up how many items meet a very specific criteria, finding the maximum value in a set of data, finding the minimum value, and finally, calculating an average. And what's really fascinating here is how these tasks constantly build on top of one another to solve much more complex problems. Let's look closely at the logic behind finding a minimum value. There is a massive beginner mistake here, and that's automatically initializing your variables to 0. If you're writing a program to find the lowest height among, say, 30 students, and you start your minimum variable at 0, your code is going to fail. Why? Because no student is shorter than 0 centimeters, so the minimum value will just remain trapped at 0 forever. You absolutely must initialize your variable with a value much higher than any expected input, like 3,000 centimeters, so that the very first real input immediately replaces it. Let's move to our final common task and see how these concepts build together so beautifully. Finding an average is really just a combination of the first 2 tasks we discussed. Inside the loop, you maintain a running total of the inputs. That's your totaling. Also inside the loop, you maintain a running count of exactly how many inputs have occurred. The real magic happens outside the loop, once the iteration is totally finished. You just take your final total, divide it by the final count, and boom, you have your average. Let's test this logic with a real-world scenario from the source material. Imagine we have a system controlling cargo crates being loaded onto a barge. The barge has a strict maximum capacity of 1,000 kilograms. So why must our iteration check a crate's weight before loading it? Well, think about it. If we use a post-condition loop that checks the weight after loading, we might accidentally load a 500-kilogram crate onto a barge that already has 900 kilograms on it. The loop would then calculate the total is 1,400, realize we've overloaded the barge, and now someone has to go out there and manually unload the heavy crate. A while loop checking the criteria preload prevents that whole disaster entirely. And that leaves us here. We've seen how for loops execute with absolute precision, how while loops handle the unknown, and how nesting selection creates dynamic intelligence. Iteration really is the workhorse of computer science. So I'll leave you with this provocative thought. Take a look at the tedious, manual processes in your own daily life. What real-world repetitive problem around you could be solved instantly if only you apply the right loop? Thanks for joining me on this explainer, and hey, keep coding.